There we go. Okay, so we are on page 26. And if we have a gas in the equation, we can measure a change in volume, change in pressure, change in mass of the system. But we look at our first equation and we say we have a solid, aqueous, solid. So we are not going to be able to use any of the change in volume, pressure, or mass of system. So far, so good? Okay. Second thing we can look at is we can say, is there something where I can measure a change in concentration? Okay, and we are specifically looking for probably a change in concentration of hydrogen or a change in the concentration of a colored substance. Okay, I'm going to leave it at that, but it is possible to do changes in other concentrations, okay? But usually we're going to be looking for either hydrogen or a colored substance. So are any of those going to do us for this particular reaction? And we look and we say, oh my gosh, look, this thing is blue. Okay? So we could measure a change in the concentration of, and now this is where you need to be familiar with your net ionic equations and complete ionic equations. So if we were to quickly write the complete ionic equation for this, it would be Cu plus 2Ag plus 2NO3 minus goes to Cu 2 plus 2 NO3 minus plus 2 Ag. All right, so we could measure a change in the concentration of copper 2 plus because copper 2 is the substance which is blue. Now, do I expect you to know that? To be honest, copper 2 being blue is so common that you should just know it, okay? So copper 2 is blue, and it rhymes. Isn't that nice? Copper 2 is blue. Roses are red, copper 2 is blue, all right? It's almost Valentine's Day. I'm sure someone could make a nice poem out of that. All right, copper 2 is blue. So we should see a change in the color of the blue. And this is easy to measure. Because copper 2 is blue. And when we say copper 2, we mean Cu2 plus aqueous. So number 1, we can look and see if we have a gas. Number 2, we can look and we see if we have a concentration that is changing, especially either hydrogen or a colored species. The third thing we're going to look for is we are going to look and see, do we have a solid that is changing in mass? Do we have a solid? Yeah. Okay. And it's often quite difficult to collect the solid that's being formed. So if I had to choose, I would probably choose the metal that I'm starting with, and I would probably choose the change in copper the mass of copper solid. Those are not the only two answers. You could also, okay, these just aren't as nice because it's harder to measure them. But also, okay, you could measure a change in the concentration of the silver ion. Okay, you go from having more silver to having less silver. But now we don't have a color change. So you would be stuck probably doing a titration, which is awkward and unnecessary. But if you wrote this as your answer, that would be fine. Okay? Or we could also do a change in the mass of the silver, which is also solid, Ag, solid. But like I said, it's often hard to collect all the stuff, all the silver that's made without also collecting the copper. Like you kind of end up with both of them in the same place and it's hard to separate them. So it's easier to collect the copper afterwards because usually it's one piece, but the silver kind of gets made in little bits and bobs. So it gets kind of mixed in with the copper. So it's a little bit more difficult. Okay, in our next one, we have, oh look, we have a gas. Yes? So we have to ask ourselves, is there a change in the number of moles of gas from side to side? Over here, we have 1 mole of gas. And over here, we have 1 mole of gas. And where am I getting these ones from? It's because the coefficients of each of these are 1. Okay? So here we also have 1 mole of gas. So in my reactants, I have 1 mole in total. And in my products, how much do I have in total? I have 2 moles of gas. More gas particles take up more space. And if you're not familiar with MC, that's my abbreviation for molecule. So more molecules take up more space. Therefore, we could measure a change in volume. Yes? Would volume be increasing or would volume be decreasing? Volume would increase as time goes on. Because we're going from smaller number to a larger number of moles. We could also do a change in, what's another good thing to measure for a gas? A change in pressure, yes. Will pressure increase or decrease as time goes on? Tell your partner. Pressure is caused by particles bashing into the sides of a container. Okay, that's what causes pressure. Pressure is caused by atoms or molecules bashing into the sides of a container. Oh, I've not left myself enough room. Okay, it's going to go down here. Container. If I have fewer gas molecules, or if I have more gas molecules, which one will bash into the sides of the container more? This is not a hard question. Second one, yes, because if you've just got, I mean, if I had 3 people blindfolded wandering around this room, let's just pretend the room was empty of everything except for the people, okay? If I had 3 people wandering around the room blindfolded, they would collide with the walls with a certain frequency, yes? But if I had 6 people, they would collide with the walls twice as often. And if I had 9 people, they would collide with the walls 3 times as often. So the more gas molecules you have, the more you have the molecules, the more molecules there are bashing into the sides of the container, so the higher the pressure. So the greater the number of gas molecules, the more frequent the collisions with the walls of the container. And therefore, the greater the number of gas molecules, more frequent, and therefore, the greater the pressure. Is that making sense? Okay, so when we go from reactants to products, we go from having fewer molecules to having more molecules. Since there's more molecules, there's more collisions with the walls of the container. Since there's more collisions with the walls of the container, the pressure is higher. So we go from having a change of volume, a change in pressure. Now let's consider our third thing here. If we have a gas, can we look at the change in the mass of the system? Now remember, when we're looking at volume, is that going to have to be a closed system or an open system? Closed. Because otherwise it'll just escape and you won't know how much volume you have. Pressure has to be a closed system, because otherwise how are you going to measure how much is bashing into the sides of the container if it just escapes the container? But if you're looking at the mass of the system must be open so that a gas can escape. But let's look at the system that we are looking at. We have a gas, and we have a gas, and we have a gas. How well is a system like that going to do if it is open? Not very well. Not very well, because everything's just going to be like off into the atmosphere. They're going to stop reacting with each other because it's not contained. If you have a completely gaseous system, it has to be closed, because otherwise everything will just escape hither and yon and everywhere. Everything everywhere all at once. Yes? Okay. So we could not, for this one, do a change in the mass of the system, because that requires one gas to be escaping and everything else to be sitting nicely in a beaker. And there's nothing to sit in the beaker in this one. Okay? Is there anything else we could measure here in this system? We could measure the green color. Okay, we could measure a change in the concentration of Cl2. Even though it's a gas, if we had it in a, like if we had it in a trap sort of a thing and we could shine the light through it, we could measure its absorbance. Okay, so we can measure a change in the concentration of the Cl2 gas. Gases also have concentrations, okay? And we would do that by looking at the color. Oh, I never did finish that sentence. Change in pressure, what would happen to the pressure over time? Would it increase or decrease? Pressure will increase as time goes on. What will happen to the concentration of Cl2 as time goes on? What will happen to the amount of green stuff? It will increase or decrease? As time goes on, will we end up with more green stuff or less green stuff? Remember, Cl2, is it a reactant or is it a product? It's a product, so are we making it or are we using it up? We are making it, so will we end up with more or less as time goes on? More. We'll end up with more as time goes on because it is a product. Okay? So it increases as time goes on because Cl2 is a product. So it is being made. Please let me know if there's any areas of this writing mess that I've done that you would like me to go to. Yes? Like here? Like here? You can still see that? Yeah. Okay. Like there? A little down? Okay. The other thing is too, you guys know how to go find these notes, right? Online? On our team? Do you remember how? Yeah. If we go to our team, how would we find these notes? Where would we go? Would we go to class notebook or would we go to class notes? The one that says use this one. Yes, class notes. Use this one. Yes, and we would go, oh, look, here it is. Oh, that's Chem 11. Oh, that's because this is my Chem 11. Let's go to Chem 12. Okay, class notes, use this one. Hey, I put it up. I did, I swear to God. I've done it twice now. Okay, you know what? I'm just going to do it right this second. Doesn't matter. We'll just do it right now so that it is here. Let's grab that. Share this notebook. And I want to... No. Actually, I just want to get a sharing link. That's what I want to do. I have no idea because you're the first person on the list. I don't know. Control C. Control V. There we go. Let's see if this works. Post. Click. Look at that. Okay, and now we say we are block 7 and we're doing the kinetics unit. So this is block 7, that's block 8. You can look at block 8 stuff. It's just a different perspective, right? We're doing the same thing. And we go here and we say we are now working on 1.1C. Look at this. So if you ever miss, oh, look, here's everything from today. Yes? So if you ever just want to go and check it out, you can definitely do this. And if you're like, I would like this to be bigger, if you click on the little bookshelf up here, you can get rid of the stuff on the side and you can have a bigger screen. Okay? So that's just, not that I don't want you to copy it down right now. I'm just saying, like, should you ever have, oh, where are we? Should you ever have a desire to like not write so fast or whatever, you certainly can do that, okay? Okay, I'd like to look at D, because D actually brings up some good points. Okay. So I would like you guys to look at D, and if you've not done this already, I would like you to say, what could I measure? Is there any gas in part D? Nope. So we're not going to be looking at volume or pressure or change in mass of the system. Okay. Is there a solid? Yes, there is. So we could say how much solids over how much time. Okay, we could say we could do the change in the mass of, and that's our solid right there, BaSO4 solid. So we're looking for gas, or we're looking for solid, or we are looking for things that have a easily measurable concentration. So we're looking for hydrogen or something colored, and as a last resort, we'll do something else that has a concentration. Is there anything in this equation that has an easily measurable concentration? And this is where you need to be thinking about your ionic equations. Because what is H2SO4 really? 2H plus SO4, 2 minus. It's an acid, yes? I have barium hydroxide, which is aqueous. And so that's an ionic compound, right? And so it's going to become Ba, 2 plus 2 OH minus. You'll notice I'm not writing my states. I'm just assuming that you know that they're aqueous if I'm writing them separately, because we're just doing it really quickly here. We have BaSO4 solid. Does that stay together or does it come apart? Stays together, BaSO4. And then we have 2H2O. Does that stay together or does it come apart? Stays together. Water stays together. 2H2O. So we could measure the change in the mass of barium sulfate. Is there anything else that is changing in concentration? Tell your partner. And remember, you want to look for things that are convenient. You want to look for things like hydrogen ion. Why is hydrogen ion convenient? Because we can use a pH meter. And we're looking for something that's colored, which we may or may not have. Do we have any ions in here that have a color? And you don't have to look and say, I don't know, do they have a color? Because if it has a color, we will tell you. It will be written, it will say blue or it will say yellow. Does anything have a color? No. Do we have hydrogen though? Yes. So we could measure a change in the concentration of the hydrogen ion. Okay. Could we measure, so that's a really good one. Could we measure a change in the concentration of SO4 2-? I mean, I know it's not as convenient, but could we do it if we had to? Is SO4 concentration changing? Here's SO4. It is aqueous. Here's SO4, but it's part of BaSO4. It is solid over here. So is the SO4 concentration changing? Yes. What's it doing over time? Is it increasing or is it decreasing? Concentration of SO4 is, this is a reactant, right? It's on the left-hand side. Do reactants get used up or do reactants get produced? They get used up, so its concentration will be decreasing. Because it is a reactant, therefore it gets used up. Could I measure a change in the concentration of water? It's a bit of a trick question. Who is the solvent in this system? Water. Water is the solvent. So what we have is we have a beaker and we have water molecules. I'm going to make them blue, okay? Whoops. Wow! Doesn't like that. Here's all my water molecules. Okay? I could be here till next Thursday doing this, yes? Because the whole thing is basically just water molecules, yes? So if I make an extra, and I am making water here, yes? I am making water, it is a product of this reaction. But if I make an extra water molecule, and I'm just showing you the one there, in a different color, but I should really be showing it in the same color. Here, let's watch what happens when I add it in the same color. Oh, oh, oh. Is the concentration of water changing? No, because it is the solvent. It is present in such high amounts, we can't measure its concentration. We can only measure concentrations of solutes, things that are dissolved in the water. You cannot measure the concentration of a solvent, okay? Water is the solvent. Therefore, we cannot measure its concentration. It doesn't have one. Yes?
Is this the same reason why you can't measure the volume of water?
Yeah, exactly. It's the same reason you can't measure the volume of water. Here again, we might say, oh, can I measure the volume of water? It is a liquid. I am getting more of it. But how much more compared to the volume? You know, like it's such a small amount. Okay. So this one is, this is answering the question, could we measure the volume of water? So we're saying, no, you cannot measure the concentration of water. In the next question, we're asking, could we measure the volume of the water? The water being made is tiny amount in comparison to the volume of water that's already there as a solvent. Right? Therefore, it is insignificant. So the answer is no. What about measuring? Yes, sorry.
You can also measure the change in concentration of BA2+.
Yes, we could also measure a change in the concentration of Ba2+, yes, because it is changing in concentration and it would be decreasing, yes. What would be wrong with measuring the concentration of copper solid? Because it's a solid. Do solids have concentrations? No. Okay. They have a density, but it never changes, right? Because that's their density. I just want to do one more from the next page because it does bring something into focus. I'm going to give you some choices here, and you're going to say which ones we could do. Out of those 5 choices, which one or ones do you like? Which ones would be possibilities? Do we like option 1? Or we don't know yet? You don't like option 1. Why don't you like option 1? You think it's a spectator ion, and I think you are absolutely correct, because if we were to take our two aqueous compounds here, and we said, okay, I got K plus, and I got I minus, and I got K plus, and I got Cl minus, and nothing changes in the K. So no, it's a spectator. How about I minus? Could we do it?
No reaction.
What? No reaction? Why no reaction? Well, that doesn't matter, because we've produced I2, which is not an ionic compound, so it doesn't split apart. Yeah, it's like when we form H2O, it's a molecule. So formation of a molecule will also mean there is a reaction. Yeah? Okay. I know it's a little complicated. So it's when you have a double replacement and you get no solid formed that you would have no reaction. But this is a single replacement, so we are going from having I minus to having I neutral. So there is a reaction there. Yeah? So it's only when we're looking at double replacement that if there's no solid form, there's no reaction. Only double replacement. Okay? I minus, could we measure concentration of I minus? Yes, we could, because it starts as I minus, it finishes as I0. Could we measure concentration of Cl2? We start with Cl2 and we finish with 2Cl minus. Has that changed? Yes, because it starts as neutral and it finishes as negative. So the answer is yes. How about I2? Could we measure a change in concentration of I2? Yes, for the same reason. I starts as negative and it finishes as 0. So yes. How about a change in the concentration of chloride? Yep, because we start at 0 and we finish with a -1 charge. Out of those 4, which one do you think would be the easiest to measure? Chat with your neighbor. Out of those 4, which one would be the easiest to measure? Remember, when we're measuring concentration, what are the 2 things that are easiest to measure? Hydrogen or a colored substance, because we can use that spectrophotometer. Do we have hydrogen? No. Do we have a colored substance? Yes. So if I had to pick out of all of these, I would pick this one because it would be easiest because it is a colored species. Okay? Does that get you guys going enough on those to feel like you understand it better? Okay. Don't be shy about dropping by tomorrow during Flex if you need any more sort of, clarification. That's the word I'm looking for. Okay, we're going to do like a little stand up and stretch because we've been sitting for a long time. Everyone stand up. Okay, here's what we're going to do today. We are going to step to our left and reach out to the left. Step to the right and reach out to the right. But now what we're going to do is trying not to bash into each other. We're going to do like a little circle and then back and then circle and then back. And we're going to speed it up a little bit. And now you're going to look in the direction of your hand. It's like interpretive dance, right? But it's actually quite relaxing. And now what you're going to do is you might have to keep your hands close to your sides so you don't bash into the desk, but just do some gentle torso twisting. Oh, that's good. Oh, yeah, we need to do this one, don't we? Oh my God, I could just do this for like hours because my back always feels like it needs more stretching. Okay, now we're going to go forward. Oh, shake out your hands. Okay, and now we're going to jump. Jump, 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 jump. Okay, we're done now. Okay. 1.2a, page 29. Okay, we get to watch a little video. Okay, let's see if we have sound. We do.
Meet our chemist, Harriet. She has a chemical reaction that needs to occur more quickly. Our chemist has some processes at her disposal that can help her speed up her reaction, and she knows of 5 ways. And to remember them, she thinks back to her days as a high school student, and the day she got a date for the dance. Harriet was in high school studying between classes. She had lost track of time and was going to be late to class. Unbeknownst to her, Harold, who was just around the corner, was running late too. They both sprinted to class, and as it happened, sprinted directly into one another. Now, this was no small collision. They ran squarely into one another in such a way that he knocked the books right out of her hand. "I'm sorry," he said. "Let me help you with your books." He kindly helped her recollect her belongings and politely offered to walk her to class. And you'll never guess who went together to the dance later that year. Yep, those two. So as we can see from this example, the key to getting a date for the dance is to collide with someone and knock the books out of their hands. Now, you're probably already aware that not all collisions lead to dates for the dance, thankfully. The collisions must have 2 important characteristics. 1, correct orientation that allows books to be knocked from one's hands, and 2, enough energy to knock the books out. Shortly after this incident, Harriet decided to tell me, her chemistry teacher, all about it. I noticed some interesting parallels between her story and chemical reaction rates, which happened to be what she was studying in the hallway the day of the collision. Together, we decided to set out on 2 missions. Harriet wanted to help all chemistry students and chemists remember how to speed up the rate of chemical reactions, and I, being the nice guy that I am, decided to make it my mission to help create educational environments in which more book-dropping collisions can take place to increase future chemists' chances of getting a date for the dance. In order to facilitate this improved dance date-getting process, I propose 5 changes to all schools that parallel Harriet's 5 ways to increase chemical reaction rates. First, I propose that we shrink the size of the hallways. This will make it more difficult to safely navigate the hallways and will cause more collisions than in larger hallways. And by increasing the number of collisions, we increase the likelihood that some of those collisions will have the correct alignment and enough energy to create a date to the dance. Now, chemically speaking, this is equivalent to lowering the volume of a reaction vessel or a reaction mixture. In doing so, the individual particles are closer together and more collisions will occur. More collisions means a greater likelihood that collisions with the appropriate energy and configuration will happen.
I have one bone to pick with this, and this is that they're showing an aqueous solution, and that won't work because you cannot compress an aqueous solution. What can you compress? Gas. Okay, so this works for gases.
Second, I propose increasing the overall population of the school. More students equals more collisions. By increasing the number of particles available for collision, we create an environment where more collisions can take place. Third, we must reduce the time allowed between classes. Heck, let's just cut it in half. In doing so, students will need to move more quickly to get from one class to the next. This increase in velocity will help make sure collisions have the appropriate amount of energy necessary to ensure book dropping. This is analogous to increasing the temperature of the reaction mixture. Higher temperature means particles are moving faster. Faster moving particles means more energy and a greater likelihood of reaction causing collision. Fourth, students must stop traveling in packs. By traveling in packs, those students on the outside of the pack insulate those in the middle from undergoing any collisions. By splitting up, each student has more area exposed that is available for a collision from a passing student. When particles travel in packs, the surface area is very small, and only the outside particles can collide. However, by breaking up the clumps into individual particles, the total surface area is increased, and each particle has an exposed surface that can react. Fifth, and finally, we hire a matchmaker. Is this colliding and book dropping too violent? Is there an easier way to get a date that requires less initial energy? Then a matchmaker will help with this. The matchmaker makes it easier for a couple to get together by coordinating the match. Our matchmaker is like a catalyst. Chemical catalysts function by lowering the activation energy. In other words, by lowering the energy required to start a reaction. They do this by bringing two particles together and orienting them correctly in space so that the two can meet at the correct configuration and allow a reaction to take place. So, to sum up, if a future chemist wants a date for the dance, he must collide with another person and knock the books out of their hands. And if a chemist wants to make a chemical reaction occur, the particles must collide in the correct orientation with an appropriate amount of energy. And both of these processes can be accelerated using the 5 methods I've described.
Now, what I'd like you to do is I would like you to tell your partner what are 5 methods. Well, first of all, what's one thing that's required for a chemical reaction to occur? And then what are 5 ways you could make that happen faster? And if you don't remember them all at this point, it's okay. Just talk about what you can remember, okay? And if you're not chatting with your neighbor, you are losing out on a learning opportunity. Chat with your neighbor. Okay, are we ready to go? All right, we are on page 29, if you're not already there. Why is my pen not working? Please be good. Oh, yeah, there we go. All right, so this is what we call collision theory, and it is how we talk about factors that affect the rate. How can we make the reaction faster or slower? So when we talk about factors affecting the rate, we say, can we make the reaction faster or slower? How can we make the reaction faster or slower? So what it all comes down to is that in order to react, particles must first do what? They must collide, right? You can imagine if I have this pen over here and this pen over here, and the reaction is for them to swap caps. If they never touch each other, how are they going to swap caps, right? It just doesn't happen. The particles need to actually be in close proximity to one another. So that is the first idea of collision theory. So that's number one. For a reaction to occur, particles must first collide. And this is what is known as the basic premise of collision theory. Now, what is a premise? A premise is just an idea. So this is the basic idea of collision theory. Now, once we have the basic idea, we can add on to that. What were two ways that the students needed to collide in order to get a successful date? They needed to be facing the right direction. They had to collide head on, okay? And they needed to collide with enough energy, enough speed, okay? So speed and energy are really connected to one another, okay? As the speed goes up, the energy goes up. So they need to have the correct, and the language that goes around this is the correct geometry. Okay, so if I'm trying to get these pens to swap caps, do you think this is going to be a good geometry for that to happen? No, because the caps are nowhere near one another, yes? So you would probably want them to collide like this so that the caps are close to each other. This would not work, this would not work, this would not work. All of those are not working. It has to be one very specific orientation. Okay. So the word that we use is the correct geometry, or we can say the correct orientation. Either of those will do. The other thing they need is, let's just say we have these two pens and they do manage to collide and they just kind of bump into each other like, oh, what happens? Nothing. Because in order for these two guys to react, we need them to collide with enough energy, bam, that it actually breaks the bond here and breaks the bond here. Bond breaking always requires an input of energy. Okay, so bam, the bonds break. And then once these are like a little bit separated, they can then recombine in a new way. Okay? But if we don't have enough energy, then they're not going to be able to break apart. They'll just bump into each other and move apart again if they don't collide with enough energy. So they need sufficient energy. What does the word sufficient mean? It means enough. Now, I will tell you that even though we have said this, sufficient means enough, I will get students, at least one of you, will say the collision needs enough sufficient energy, which means it needs enough energy. Yes? And don't worry, I mean, even in my AP class, these are like supposedly the biggest brains, right? I had at least 2 people tell me enough, sufficient energy. And I'm like, really? Really? Did you really? Anyway, whatever. Okay. So a couple other words we need to look at. So we've learned the word geometry, which is the orientation. We've learned the word sufficient, which means enough. And we've also learned the word for a collision to be successful. If a collision is successful, it results in a reaction. So a successful collision results in a reaction. You can have a collision which is unsuccessful, which does not result in a reaction. Another word for successful is effective. Okay? Those are the same. Successful collisions are effective collisions. Now, according to collision theory, the greater the frequency of the collisions, so the greater the number in a certain amount of time, so the greater the number of collisions in a given amount of time. Whoops, Givens has an E, I not an E. The greater the number of collisions in a greater amount in the same amount of time, the faster the rate. So that's like if we can get more students colliding in the hallway within the same period of time, we will have more dates to the dance. Also, if we can increase the energy of those collisions, so if we're making the particles move faster, then we can get a faster rate because we're going to have more collisions which are successful, more collisions which are effective. So, what were the things they talked about? Well, they talked about squeezing the building. I'd like you to look at these and decide which one sort of correlates with squeezing the building, making the hallways smaller. There's actually a couple that we can go with here. So probably squishing would be the closest to changing the... It could change the concentration, but probably it's closest to changing the pressure/volume because we're really looking at the size of the hallway. Although it could also change the concentration, it could be. Okay, so pressure volume is like changing the size of the hallway. So just like when we had our maybe 3 particles in a container, and they had a certain number of collisions with the walls of the container, if we make the container bigger, what would happen to the number of collisions with the wall in a given time? It would decrease. But not only do the collisions with the wall decrease, also the collision between the particles themselves decreases. Okay? I need an eraser. There we go. More collisions in a given time. Fewer collisions in a given time. So one of the things they did was change the size of the hallway. That correlates to the pressure volume. What was another thing that they did? They added more students. Which one of these correlates with adding more students? Tell your partner, which one correlates with adding more students? Adding more students would be like increasing the concentration. Because you have more particles in the same amount of space. And what will that do to the frequency of collisions? Will it increase or decrease? If you add more students, it will increase the frequency of collisions. Yes. What was another thing they did? Well, no, they didn't do that in the school. What did they do in the school? They separated the students who were in a group. So they unclumped the students. Which one is that? That is our surface area. Okay, this is like where we separate the students in a group, and therefore we expose the students in the middle so they can also collide. So we could add more students, we could increase the concentration, that increases the frequency of collisions. We could change the size of the hallway, we could squish the hallways, which would change the pressure or the volume, and that would mean that we would have more frequent collisions. We could change the surface area, which means there's more students exposed and able to collide. So we've increased the frequency of collisions. What was another thing that they did in the video? They had a matchmaker. Which one of these things is a matchmaker? That's the catalyst. And what the matchmaker does is the matchmaker says, rather than having to randomly collide with each other with a certain amount of energy, I'm going to take the work out of it for you. I'm just going to grab you and put you together. Did you have to collide with a whole bunch of energy? No. So what it means is it lowers the amount of energy needed. And so more students, you could just be walking along. You could be just like a little student walking along really slowly, okay? Or we could have our pens moving really slowly, yes? But the matchmaker says, oh, come along, here we go. And the catalyst actually helps with this process, yeah? It helps break the bonds. So it helps align the particles and break the bonds so that they don't need as much energy. Therefore, any old particle moving at any old speed might be able to react. Whereas if you want them to react without the catalyst, they have to, bam, really fast. Yes? So this one lowers the energy needed for the collision to be successful. What was another thing they did? Yes. Yeah, they made the time between classes shorter, so the students had to move faster. Why is this not moving for me? Hello. It really doesn't want me to. There we go. So the time, BW is between. And if the students move faster, what will happen to the energy of the collisions? Let's imagine you guys are like slowly walking around the empty classroom blindfolded, and you might collide with people with a certain frequency. What if you all of a sudden started running around the classroom? Would you collide with less energy, more energy, or the same energy? You would collide with more energy. And you would also collide more frequently. Okay, so your homework. 1, study for your quiz. And 2, you're going to read pages 30, 31, 32, and 33. Yeah, if anyone needs their Mountain Madness form signed, I can do that for you. Okay. Hello.
Question.
Yes.
I was doing the homework, right?
Yes.
So I was a little confused because when we had these, we had, I don't know, it was like structured differently than like what you wrote for these things. I was like, am I doing it correctly or no?
Well, did you look at the answer key?
Yeah.
Okay. So could we have a change in volume?
Yeah.
Oh, okay. What else did you say? Jan, what does that say? Pressure?
Yeah.
Yeah,
Gas.
absolutely. Absolutely, because we're making a gas.
Right?
Yeah. Okay. Or you can measure the mass of the, I would say the mass of the system would be easier because you just stick it on there and then the mass gets smaller because the gas shakes. It's hard to measure mass of a solid, especially because these two kind of look similar, right? And you're like, which one do I have? I don't know.
I was doing the homework over the weekend.
Yeah.
I found I had like the most like difficulty with these.
Yeah, but yeah, it looks like you're doing okay. Yeah?
And I don't know, this one's like just the same thing. Like if it's a solid, then you can like weigh it or
Yep.
something like that.
Yep.
Since it's a gas, you can just like, balloon, plug it in.
Yep.
Good.
Just right. 7.
Oh my god. And then this.
And then that one there. There you go. Oh, that's the teacher in charge of the field trip. They're supposed to sign there.
Sure.
That, yeah. This one down here.
Oh,
Teacher.
I can get it.
That's okay. You can pretend I'm in charge of it.
Alright, and then number 5. I don't.
You don't need
have
to
this?
do.
Okay.
There you go.
Yeah, I'm a little kind of scared for this.
Yeah, no. Just leave that out.
Yeah.
Yeah.
So just review. You just keep on reviewing.
Yeah,
these things.
just review those.
Okay.
Yeah, you're good.
Okay,
Yeah,
thank you.
yeah.
Will there be like extra practice you'll post? Like,
It's really hard to come up with questions. So that's it. I've come up with all I can come up with.
okay. All right, thank you.
Okay? Yeah.
If I leave like 10 minutes early.
Yep. No problem.
I need to work at the school store.
Yeah.